Good evening to one and all present here. Hope you all are safe and sound. On behalf of ISI Bangalore students, I welcome all participants to the sixth day of the Mathematics Online Camp. I have great pleasure in welcoming today's speaker, Professor Kapil Hari Paranjape, to this platform. Professor Paranjape obtained his MSc degree in mathematics from IIT Kanpur. He was awarded his PhD in maths in the year 1992. He has previously been a professor at ISI Bangalore and Institute of Mathematical Sciences, Chennai, and is currently a professor at Eisenhower. Professor Paranjape was awarded the Fellowship of Indian Academy of Science in 1997 and Fellowship of National Academy of Sciences in 1999. He is also a recipient of the Shanti Swarup Bhatnagar Award. His interests are centered on algebraic geometry and the study of algebraic cycles. With great pleasure and honor, I welcome the Honorable Professor Dr. Kapil Hari Paranjape to speak on the topic using regular polygons to solve equations. Before we begin, I request all participants to keep their mics muted unless any questions, in which case they may unmute themselves and ask or type them in the chat. Sir?
Yeah, thank you. Thank you for the kind introduction, and thank you for the opportunity to give a talk here uh, in spite of the strange situation in which we find ourselves. Today, my talk is about using or trying to understand what is the connection between regular polygons and solving equations. Okay. So, let me begin. Yeah. So Gauss proved that regular polygons with n sides can be constructed using straightedge compass only for some n. Maybe you have heard of this result. I will speak a little bit more about this. And to prove this, one studies algebraic equations in one variable in the way set out by Abel, Galois, and others. Of course, Gauss was the pioneer, but the approach we nowadays follow is mostly due to Galois. Galois extended Abel's and Gauss's results to show that many and most, in fact, most equations of degree 5 or more cannot be solved in terms of kth roots of numbers. Okay. Reversing this story, we can ask which equations can be solved in terms of regular polygons of various sizes. Okay, so that's a reverse question that we know that all equations cannot be solved. The question is which ones can be. And this question has a neat answer due to Kummer, Kronecker, Weber, and others, which we will discuss at the end. Okay. So first of all, one wants to see what is the connection between algebra and geometry. So Gauss was perhaps the first to realize that straightedge and compass constructions can be used to carry out arithmetic operations on points in the plane. Okay. So to do so, you fix an origin, which we denote by 0, and a unit vector, which we denote by 1. Okay. And then I want to say addition is carried out by vector addition. So here is 0, and here is one vector, alpha, and then here is another vector, beta. And as in order to carry out alpha plus beta, you just take the parallel line through this and take the parallel line to that one through this, right? So you make a parallelogram, and at this point will be alpha plus beta. Okay. So that's the, or rather, if you want to be very precise, this vector, right, will be alpha plus beta. So that's how vector addition is carried out. But in fact, you can not only do addition, but you can do multiplication. So multiply two vectors. So again, but then you need the unit vector, right? So suppose this is the unit vector, and you're trying to multiply alpha and let's say beta. I'm not sure I'll be able to do this. Maybe I will treat this as the unit vector. Okay, and call this alpha, this beta. Okay. So the idea is to use similar triangles. Okay, and so I want to construct a triangle similar to this one, but starting at beta, right? So how do you do that? Well, so you need to take a line which is similar to, sorry. So first of all, you want to mark out alpha here, 1, right? So distance 1, and then you want to construct a line parallel to uh, to, to you transfer this angle here and construct a line like this by constructing a similar triangle. Okay, so this length is same as the length of alpha, and this angle is the same as this angle. Right? And then you draw the line parallel to this one, right? Parallel to this, and this point will be alpha times beta. Okay. So you have to let me just say it in words here, that addition of the angular displacement, that is first what we did, and then we also made sure of the multiplication of the magnitude, right? So this length is 1, this is the same length as this, and so this length will become, and this length is alpha, so by similarity of triangles, this length will be the same as the length of alpha times the length of beta. So anyway, so I hope uh, you know enough high school geometry to be able to carry out this construction with ruler and compass. So the whole point is that addition and multiplication, all these constructions using straight edge and compass. Right? So you can add and multiply, and of course you can also do the other operations. Right? It's not scrolling properly. Okay. So note that these operations can be carried out using straight edge and compass constructions, and subtraction and division can also be carried out. In other words, we have what is called a field. A field is something where you can do the usual arithmetic operations, addition, multiplication, subtraction, and division, following the usual rules, except that, of course, division should be by non-zero elements, which is also a usual rule. Now, the most important observation here is that constructions using straight edge and compass are equivalent to solving linear and quadratic equations. Okay, so this is not too difficult to prove. Uh, in other words, what we are saying is that if you have constructed complex numbers alpha and beta, so now from now on, I will think of complex numbers as points in the plane, right? With the addition and multiplication, which I just talked about. So geometrically, that's the way to think about it. And we can construct the solution of x equal to gamma of the equation alpha x plus beta equal to 0 when alpha is non-zero. And we can also construct the solutions x equal to gamma. There are two solutions, x equal to gamma 1, x equal to gamma 2 of the equation x squared plus alpha x plus beta equal to 0, where alpha and beta have already been constructed. So the idea is that you can keep building on the constructions, that if you are given the construction of alpha and beta, then you can construct solutions to these two types of equations. Right? So note that therefore constructible numbers form a field which is contained in the field of complex numbers, because the first equation says that you can do division and subtraction. Right? If I'm given alpha and beta, and if I can solve for x, that means I can subtract and I can divide. So this is so the question is how big or what is this field, right? So remember that Descartes was the first to suggest that algebra is used to study geometry using coordinates, right? Of course, now we are not using what are the usual coordinates, so to speak. We are using complex coordinates, but that's okay. This does not mean to suggest that geometry is replaced by algebra. Okay. On the other hand, whatever construction we have done does not mean that algebra is replaced by geometry, right? So in some sense, the whole idea is that algebra and geometry play with each other, right? So of course, one way to think about how high school analytic geometry problems can be solved using algebra is by converting them to algebra using Cartesian coordinates and then trying to solve the corresponding algebra problem. Conversely, if you started with some algebra problem, you can convert it into a problem in geometry by using Cartesian coordinates and then try to solve the geometric problem, right? So which way you want to do it, you use the one which gives you the most insight, right? So this subjective choice. Some people like algebra better, some people like geometry better, and some people manage both, right? So great people. So Hilbert has said that arithmetical symbols are written diagrams and geometrical figures are graphic formulae. So Hilbert clearly believed that there is no difference as such. You use whatever suits you at any given time. So that's the approach that we are also going to follow. So note also that the usual numbers which we do with addition, multiplication, so-called real numbers, are also there inside this field. Okay, points on the line joining 0 and 1. So we are thinking of our plane as consisting of a center 0, remember, and a unit which is called 1, and all the addition and multiplication is being done with respect to these two things. So multiplication requires a unit, addition does not require a unit because vector addition. Okay, so, and we note that the addition and multiplication for points on the real line, though actually if you want to carry out the addition and multiplication using similar triangles for the real line, you actually have to do a little bit of jugglery because you can't make similar triangles which are all contained in the line. So you'll have to push a distance out of the line, right? So you must have seen this, that if I want to multiply uh, two numbers using drawing parallel lines, right? So what you do is you put 1 here, you put alpha here, and then though your beta is given here, you push it there, right? By using a compass, you take it there, and then you join this, and then you join the parallel line, and then you push them back to get alpha times beta. Okay, so uh, so it's not exactly the constructions using ruler and compass. One has to do a little bit of so some my lines are not very parallel. Okay, doesn't matter. Okay, so the constructions have to be done a little carefully in that case, but in any case, you can see that arithmetic of points on the line is the arithmetic of real numbers as usual, and points on the ray starting at 0 and the direction 1 are identified with positive numbers. So we have a geometric feeling about uh, the algebraic properties, and the question of positivity and so on also have been understood in terms of geometric notions. That's the point I wanted to make. That's it. Those on the opposite ray are identified with negative numbers, right? So multiplication by a positive real number gives a mapping of the plane to itself, and which is called scaling, right? So now there's this number iota. So what is the number iota? So you started with the number 0 and the number 1, and now you go exactly in the orthogonal direction, in the anti-clockwise direction, right? In the anti-clockwise direction, and this is iota. And if you look at the rules that we have given for multiplication and addition, you check that iota times iota plus 1 is 0. Right? So note that these 4 points, iota minus iota, 0, 1, iota minus 1, minus iota, they are actually points on the circle, and you get an inscribed square. Okay. So, so this is the first example of a regular polygon that you can think of, which occurs using iota. Okay. So we'll come back to this shortly. Okay, another geometric operation is complex conjugation. So reflection of the plane on the line joining 0 and 1. So you take 0, you take 1, and take any alpha, and you take the perpendicular like this and go in the opposite direction, take the reflection, and this is called alpha bar, and this is the complex conjugate, right? So it's an automorphism of the field. It preserves addition and multiplication. So it's an automorphism of the field, and that you can see because reflection preserves angles, reverses angles, and so on. So you can check that it will take addition to addition. That is more or less obvious. Multiplication takes just a little bit of work, perhaps, to check that it's correct. Okay. So it's an automorphism of the field, which we denote by alpha goes to alpha bar. And note that alpha plus alpha bar. Okay. So if you look at our figure again, then this is alpha, this is alpha bar. By the way, I've always been drawing 1 in the usual x direction, but 1 can be any vector, actually. It's just a convenience that we write it like this. And then we are going to take the parallelogram, and we are going to, because of reflection property, we'll see that this will be alpha plus alpha bar will be a real number. And similarly, alpha times alpha bar will also be a positive real number. So the way I drew it, of course, alpha plus alpha bar will also positive. But if your alpha is in this direction, and then alpha bar will be in that direction, and then alpha plus alpha bar will be alpha plus alpha bar will be here. Okay. So it won't be in the positive direction; it will be in the negative direction. This is 0. Okay. So alpha plus alpha bar need not be positive, but alpha times alpha bar is always a positive. So this is some elementary thing you can just construct and so on. Okay. Now every complex number can be written in the form x plus yi, where x and y are real numbers. Again, you can easily check this. This is just the coordinates on the plane, Cartesian coordinates. And if alpha is x plus yi, then norm of alpha, which is alpha plus alpha times alpha bar, you can check. It turns out to be x squared plus y squared. Basically, the point is that x plus yi bar is x plus y, x minus yi. And when you multiply them out, you get x squared plus y squared. So the points with norm alpha equal to 1 can be identified with points on the unit circle. Okay, so and note that norm alpha beta is norm alpha times norm beta. So the product of 2 points on the circle is another point on the unit circle. So this, you'll see, this is quite important. Okay, so I want to underline this, that the unit circle has the property that multiplication of points on it is another point on it. And in coordinates, you can write this in this form, that x plus yi times y plus uv is
Hello, sir, you are not audible.
Okay, sorry about that. So I think you need to give me permission again to share screen. Okay.
Yes, sir. I've given.
Yeah, yeah. Okay. Okay, so I don't know how much was audible before we got cut off. So let me say it again. So on the points on the unit circle form a group, okay, is what you're going to say is that you can multiply 2 points on the unit circle and you can get another point on the unit circle. Points on the unit circle are those whose norm or n alpha is 1. Okay. So they are solutions of the equation x squared plus y squared equal to 1. And they note that this is a very interesting identity because it holds whenever you have 4 things for which you can define multiplication, addition and multiplication commute. So for example, this identity holds with, maybe I'll just say a few words about that. Let's see, how do I get to the other one? I don't see. So anyway, so what I wanted to say is that, for example, you can see that you know that, let's say 3 square plus 4 square is equal to 4 square is equal to 5 square, right? So now, right? So anyway, so I don't know what I'm trying to say here. No, maybe I wanted to say that, yeah, 1 square plus 2 square is 5, right? And maybe something like what is another example I can think of? 2 square plus 3 square, let me say, or 2 square plus 3 square is how much? Is 4 plus 9 is 13. And so you can see that this means that 65 can be written as sum of square. Of course, you know that 1 square plus 8 square is 65, but you can get other examples which are not so easy to write down. Okay, so the point is, this is actually a very interesting identity which has a lot of number theoretic implications, because it says that the product of a sum of 2 squares is itself the sum of 2 squares. So maybe I'll write that sentence down here. So So that's an interesting identity, and in fact, it is very interesting to know that you can actually replace 2 by 4 as well. In other words, if I have the product of the sum of 4 squares, then it is in fact the sum of 4 squares. Okay, so that's one of the beautiful identities which is due to Lagrange maybe, and then later expanded by Hamilton. Okay, and working with coordinates. Okay, right. So where was I? Yeah. So given a complex number, eta on the unit circle, what is the operation? Alpha goes to eta times
Sir.
alpha. Yes.
Sir, the property you said about the unit circle, that product of any 2 points on the unit circle maps to another point in the unit circle.
Yeah.
So can it be proved geometrically without any algebra? Like using geometry only?
No, well, it depends. So if you're just seeing it geometrically, maybe I should do it. Okay, let me do it here. So it depends. How did we define multiplication? Okay, so this is 0, this is 1, and multiplication was defined by, you suppose this is angle, then I must rotate this by the same angle, right?
Yes.
And the magnitude is multiplied, magnitude anyway is 1. So of course, again, I'm going to get a point on the unit circle. Okay. So this angle is alpha, P, and this angle is Q, then this angle is P. Okay. And so this total angle is P plus Q. Okay, so it's just, so as you'll see, in fact, you can see it as rotations. Okay, so you can think of points. Let me just continue and you'll see immediately why it's
independent fact. It's not only, it's the independent fact. Yes.
Yeah. Just a geometric construction. Okay, you can prove it directly that multiplication by a complex number on the unit circle, then the operation alpha goes to eta alpha, and suppose P denotes the angle between eta and 1. This is just what I was saying. This is 0, this is 1, and this is eta. This angle is P, then, and this length is 1, right? This is on the unit circle. Right? Then the other operation is rotated on the plane by the angle P. Okay? So therefore, of course, it is two rotations. Composition of rotations is another rotation. Right? So that's another way to see it. So multiplication by complex numbers, you can also think of in two ways, and this is what we have been saying earlier also, consists of two operations. One is scaling by positive real numbers and rotation by points on the circle. Combined together, you get multiplication by complex numbers. You can also see it in matrix form. So that's another way to do the same calculation. So we can think of the plane as a collection of column vectors. Xy is equal to xy transpose, okay, which are the coordinates. And multiplication by the complex number a plus bi iota is then given by the matrix. You can just check that it's multiplication by this matrix. So such 2 by 2 matrices are in fact closed under the operation of addition and multiplication of matrices. Okay. And so we can think of complex numbers as can be identified with the algebra of such matrices as well. And so it is, yeah. So of course, once you say algebra, then the division requires some work, and you have to see that if AB is not 0, 0, right, then this means that A square plus B square is not 0. And so you can write the inverse as 1 over A square plus B square, right, and A against B and minus B. Right. So that's the inverse of this matrix. So division is also possible. Okay. In any case, so this is just a hint of how one should think of the points on the unit circle. And now I want to think back about the regular n-gon. Okay. So the regular n-gon inscribed in a circle consists of n equally spaced points on the circle starting at 1. Right? So if you see the usual picture of hexagon, then you're going to take equally spaced points starting at 1. Then this is the first point, the second point, so and so on. Right? And the first point in the anti-clockwise direction away from 1, and repeated rotation by that, right? So what are we doing? We are taking this point, and then we are taking this one, and then we are repeating rotation by that angle. And saying that it's regular means that it comes back to the starting point, right? So this is another way of saying that the points are given by 1, zeta n squared, zeta n minus 1, and of course, finally, zeta n to the power n is 1. Okay, so zeta n satisfies the equation t to the power n equal to 1. So the regular n-gon inscribed on the circle in terms of this complex arithmetic is the one which satisfies this equation. So it's what we call an nth root of unity. Moreover, every solution of this equation is of the form zeta n to the power a for some integer a in 0, 1 up to n minus 1. Right? So zeta n to the 0 as as usual, is going to be 1. So, I mean, that's just usual convention. Okay. So that's a regular n gone, and we have seen using algebra of complex numbers, we see that a regular n gone is amounts to the question of finding nth roots of unity. So the problem of constructing an n gone is the same as the problem of constructing solutions of t to the power n equal to 1. If you want a geometric construction, then we should solve this by repeatedly solving quadratic equations. So that is important, that geometric constructions involve repeatedly solving quadratic equations. Let's see how this works out for small values of n. Okay, so for n equal to 1, of course, we have only the trivial solution, t equal to 1. For n equal to 2, we have t equal to plus minus 1. Now what happens for n equal to 3? So now we throw away the trivial solution and we write t cube minus t cube minus 1 by t minus 1, which is t square plus t plus 1. And this is a quadratic equation. And so we can solve it by geometry to get two roots, which are usually denoted as omega square. Omega must have done this in high school, minus 1 plus square root minus 3 by 2. Right? And omega square is the same thing with a minus sign. Okay. So we can construct the regular three-gon or equilateral triangle. For n equal to 4, we again throw away the trivial solutions t equal to plus minus 1 by looking at t to the 4 minus 1 by t square minus 1. And you get a quadratic equation t square plus 1. And you can solve this quadratic equation as t equal to iota minus iota. And note that this shows that this is back to our old construction of a regular square, right? We constructed a square inscribed in the circle. Right? So the square, of course, drawn like this, right? And the equilateral triangle was drawn like this. Okay, starting at 1, we constructed these two figures, right? And both of them can be solved using quadratic equations. Okay. Okay, so I'm not going into the details of how we solve quadratic equations, but remember that to solve a quadratic equation, maybe I should have remarked on that. Let me just go back a little bit. Okay. So why can we solve quadratic equations using ruler and compass? I said that, but nobody challenged me. But it's not very difficult, right? And where is it from? Yeah, construction using stature and compass are equivalent to solving linear and quadratic equations. And so how do you solve quadratic equations? How do you solve this equation using? So you know the solutions, right? So we know that the solution is given by minus alpha plus minus square root alpha square minus square beta by 2, right? So all this addition, multiplication, subtraction, you can do. So the main thing is how do I get a square root, right? So I have to get square roots using my method. And recall that the square root involves two things. So if I want to take square root of alpha, then, and this is 1, right? So in order to get square root of alpha, what do I have to do? I have to square root the length, right? And I know how to do that, right? So I suppose all of you know that if I take a unit length here and a length some x here and take a semicircle like this and take this length, right? Then this is square root x, right? If I'm not wrong. By Pythagoras theorem, because this angle is 90 degrees, or by similar triangles. All these three triangles here are similar, and using that you can prove that this distance is square root of x. Okay. So you can construct the square root of alpha, square root of the length of alpha, right? And this angle you have to half, right? And again, we know how to bisect angles, and therefore you can construct square roots using complex numbers. So that's just the point which I wanted to make, that solving quadratic equations is relatively easy, and in fact, we all know from high school how to do those constructions. So, we can certainly construct any problem where we are solving by adjoining square roots. It's just whether you want to do a short, elegant construction or you just want to do brute force, that is up to you. Okay. So certainly the triangle and the square can be constructed. How about the next case, pentagon, n equal to 5? So now if you throw away the trivial solution, you get t to the power 4 plus t cubed plus t squared plus t plus 1. Now, of course, this is not a quadratic equation anymore. But you do obtain this identity that zeta, and written it the other way, is equal to -1, right? So 1 zeta to the 5th, zeta 5 plus zeta 5 squared plus zeta 5 cubed plus zeta 5 to the 4th is -1. Now you consider this complex number, okay? Tau is equal to zeta 5 plus zeta 5 to the 4th, and note that it's squared by just using the properties of zeta 5. Note, of course, that we also know that this implies that zeta 5 to the 5 is 1. Okay. Using that, you easily get this identity, and then you add up tau squared plus tau and you get 1. Okay, so tau satisfies the quadratic equation tau squared plus tau minus 1, and so we can construct it geometrically. By the way, this is sometimes called the golden ratio. Right? Or maybe it's minus of it is 1 minus it is called the golden ratio. I forgot it. Anyway, so you can construct this geometrically. And now, having constructed it geometrically, note that tau times zeta 5 is zeta 5 squared plus 1, right? I take tau times zeta 5, then here I'll get zeta 5 squared, and here I'll get 1, right? So tau satisfies this quadratic equation. I mean, zeta 5 satisfies this quadratic equation, t squared minus tau t plus 1 equal to 0. So we can construct it geometrically using tau, which we already constructed. Okay. So by solving two quadratic equations one after the other, you can construct the pentagon. And in fact, this is a conceptual approach to the classical construction of the pentagon, which you must have studied in school. Right? In high school geometry, one learns to construct the pentagon, and that construction is derived from this, except here we have done it algebraically, where the construction will be given completely geometrically. And by the way, it's an interesting thing that people were able to do these constructions before they learned enough algebra. So part of it, I find it curious how somebody constructed the pentagon. Was it by accident, or did they have some way of neatly thinking about it, which led them to the construction? Because of course, it is not too difficult to find some such construction as you have normally seen in high school geometry, right? So I think the usual construction is something like this. You construct a line of length 1, another line of length 1, and then this line will have length square root 5, and so I think you take an arc like this, and then this is going to be the base of the pentagon, or something like that. Okay. So this is, of course, this length is something like 1 minus square root 5, or square root 5 minus 1. Right. And so that somehow plays a role in the construction. Okay. Anyway, so that square root 5 minus 1 by 2 is the golden ratio. So somehow you have to do something with that, and then you get the pentagon. Okay. But my question is, without writing these algebraic equations, how is it clear that you should be doing square root 5 minus 1? So certain amount of trigonometry or some clever ideas are required to come up with that classical construction. Okay. So I want to now emphasize certain aspects about these solutions and everything we have studied in terms of group theory. So I want to say that when you look at a system of linear equations, when we learn how to solve linear equations, which you must have learned, there are two types of transformations that come into play. One is transformation of the system into another system, okay, which has the same solutions as S, but somehow it is simplification. It's simpler. The S prime somehow is considered to be simpler than S. So this is one kind of transformation. And the other is actions on solutions, transformation of one solution into another solution, right? So typically a linear equation, we know there are many solutions, one of which can be obtained from the other by adding some vectors, right? So those are two types of uh, ways of having certain transformations in while solving systems or equations. So when simplification of equations is useful, but of course primarily we are interested in actions on solutions. Okay, so this is the distinction, that in the case of solving linear equations, often one is focused on simplifying equations, and invertibility. Okay, so let me come to the invertibility. So the point is that such transformations should have two properties. Transformation should be inverted, right? So that nothing is lost by making. Of course, you can take a equation, you can transform it into a very simple equation by throwing away half the coordinates. But that's not the same equation. So you want to do the transformations which are reversible. Okay. And the other thing is that transformations can be combined. I don't know why I have misspelled transformations so many times on this page. Okay, maybe I was sleeping. Okay, so you can combine them, and so that simple transformations can lead to complicated ones which are not immediately obvious. Okay, so keep both of these in mind, and if you have solved the 15 puzzle or the Rubik's cube, you'll see some connection, right? So obviously, one of the things which you want while solving the 15 puzzle or the Rubik's cube is that the moves are reversible, right? But otherwise, you don't know that the Rubik's cube can be solved. Starting, if somebody takes a cube which is in the correct colors and then mixes it up, how do you know that you can still solve it? The answer is that because the transformations are invertible. And the combination is important because the simplest moves in the 15 puzzle or in the Rubik's cube seem very simple. Like they'll just move one or two cubes or one side of the cube or one or two tiles in the 15 puzzle and so on. So there's more complicated transformations should be obtained from simple ones by combination. So both of these are important, and these two properties lead to the mathematical notion of group actions. In fact, so given a mathematical structure, the group of automorphisms of S is, that should have been a different S. This S is the same. This is the collection of transformations, sigma, with the property that each transformation is invertible and transformations can be composed. So this is the so-called group of group actions. And what I want to emphasize is that this is the key idea of Galois, but of course it was kind of thought of earlier by Gauss and so on, is that we would like to understand groups of transformations of solutions. So the action on solutions is something which Galois emphasized. The simplification as a way of having group actions is already there in Gauss, right? So Gaussian elimination, we called it. Gaussian elimination is a process of applying invertible transformations. We don't change the solution, but which simplify the equation. So simplification is one kind of transformation we can do with these equations. And the other kind of transformation is some transformation which takes one solution to another solution. That is Galois' contribution, which is already there in linear equations, but it's not very serious there. Here you will see that it's more complicated. Okay. Even in situations where the second condition is not satisfied, that means that transformations can be composed. What I mean by that is we can expand the collection of allowed transformations to include all compositions, right? So simplest case is take row operations. So row operations on a matrix are obtained by composition of elementary row operations. Elementary row operations When I compose two elementary row operations, I don't necessarily get an elementary row operation. I get another row operation. But all row operations are obtained by combining elementary row operations. Sometimes the group theory part is so useful that we expand our collection of allowed transformations to include all composed transformations, right? So similarly, uh, in geometry, the basic transformation on the plane is reflection. But of course, when I combine reflections, I get translations and rotations. And so I want translations and rotations as well. So uh, this is the advantage. Once we learn some group theory, one can use the ideas of groups in a more powerful way. And so these two properties are uh, those which underline the importance of groups. Okay. So you already seen many examples of groups. So for example, the conjugation action, alpha to alpha bar is a group action. Known that alpha bar is alpha, so that this group has only two elements, identity and conjugation. Multiplication on the circle, okay, on the plane as a group of rotations of the plane. And for each n, we have also seen this smaller group of nth roots of unity. So these are some groups, and we'll see why the groups play a role for us. So the last group is somewhat special. A group is called cyclic if there's an element g, little g in G, so that every element is of the form g to the power k for some integer k. Note that we write composition multiplicatively as we have been doing here, right? So uh, we multiply two group elements, theta n to the a times theta n b as theta n to the a plus b. Right? So usual multiplication notation. Now, in the case of Cn, it is a finite cyclic group with n elements. So it is a cyclic group. Every element is of the form theta n to the power k for some k, and it has n elements. Okay. Now, if this shouldn't have been n, I think this is a. Okay, if a is an integer co-prime to n, by Euclid's division algorithm, you can write ap plus, you can find p and q integers such that ap plus nq is 1. Right? So why do I want to use this? So since g to the power n is identity, it follows that g to the power ap is equal to the g to the power ap plus nq, but ap plus nq is 1, which is g. So not only can g to the power a is of course a power of g, but this says that g itself is g to the power a to the power b. Okay, so if a is an integer co-prime to n, and you're looking at elements in a cyclic group, then g to the power a, g can be written as a power of a, g to the power a, and so every element can actually be written as a power of g to the power a. Okay, so this says that g is not special as an element of the cyclic group, even though it is a generator. There are other generators. There are many other generators, many other elements. And so the transformation g to the power k goes to g to the power ak gives an automorphism of the cyclic group. So now we are looking at remember that we are looking at groups as groups of automorphisms of some mathematical structure. Now this is our mathematical structure is cyclic group Cn, and g to the power k goes to g to the power ak is an automorphism of this structure, and it happens if and only if a and n are co-prime. So we just saw that if a and n are co-prime, then it gives such an automorphism. One can prove the reverse also. It's not too difficult. Uh, so note the composition of the automorphisms is given by a and b is just automorphism given by the product of the two, right? G to the power k equals to g to the power ak, and then that goes to g to the power a b and bak. If you like, multiplication of integers is completed. Okay. Moreover, it's clear that if A minus B is divisible by n, then they give the same automorphism, right? If A minus B is divisible by n, then this is equal to G B K, right? A minus B is divisible by n. Because G to the power n is identity. Okay. So the group of automorphisms of Cn can be identified with this new group Gn, which consists of numbers from 1 to n minus 1, with the property that their GCD with n is 1. Okay. And which is considered as a group under multiplication modulo n. Why modulo n? Because if a minus b is divisible by n, then they give the same automorphism. Okay. So this is a new group, and we are interested in this group Gn also. Now, the size of this group Gn is the number of A, such that GCD of A is 1. Number of A in 1 to n minus 1, and this number is denoted by phi n, and it's called Euler's torsion function because it was studied by Euler. And suppose that m and n are co-prime, then you can see that if A is co-prime, so basically if you're given, anyway, so an application of Chinese remainder theorem can be used to show that the GMN is made up of elements of GM and GN, where this can be thought of as so every number A, which is of this type, so that GCD of AN is 1. And what I do is I add some multiple so that this minus 1 is divisible by n. Okay. And of course, as far as this side is concerned, it's the same as this element is concerned. Gn, or okay, I should have done Kn here divisible by n. Okay. Right? And so this will give me some element, this will give me some other elements, and you can see that phi m n is equal to phi m times phi n. Okay, so this is a very beautiful identity, which is called the multiplicative property of the Euler torsion function. And Gm, as I said, so Gm can be thought of as those elements of Gmn which are remainder 1 modulo n. So which I said that minus 1, that number is divisible by n. Okay. And then you can see that there will be this identity holds. And using this identity, if I know a factorization of n into primes, then you can see that phi n will be the product over each of those factors. And now for a prime power, it's very easy to see what g of. So note that I should have said that there g of p to the power a k is nothing but take all the elements. We want 1 to p to the k minus 1 such that GCD of a and n is 1, but in our case n is p to the power k, so this is the same as saying that GCD of a and p is 1, right? Because GCD of a and p to the power k is 1 if and only GCD of a and p is 1. And that's the same as saying that p doesn't divide a. And if I look at the numbers which are divisible by from 1 to p, right? So if I take all the numbers from 0 to p to the power k minus 1 and look at the numbers which are divisible by p, that is exactly all the numbers which are of the form. You take 0 to p to the power k minus 1 and multiply them all by p, right? So this number, this has exactly these many numbers. Okay. So you get this formula, which is a very neat formula to calculate the Euler torsion function, but of course it depends on factorization. So it's not trivial because finding factorization, as you know, can be quite complicated. Okay. So now I want to connect this to this business of solving equations. Okay, so far, so I hope this idea is clear. There's something called the Euler torsion function, and the Euler torsion function has this formula. So this will play a role in what we do later. Okay, let Kn be the subfield of complex numbers generated by this zeta n. So that means the Kn consists of zeta n, and all complex numbers that arise by repeated application, addition, multiplication, subtraction, and division. Right? This is called the cyclotomic field. Right? So it's so Gauss proved some theorems about the cyclotomic field, which I'm not going to prove here. It will take too much time. Uh, and so here I've said P, but P is not a prime. Okay, just be a little careful. So Gauss showed that Kn consists precisely of the numbers of the type sums of zeta n to the power k, where k goes from 1 to phi n minus 1. Okay, so that's important, that every number can be uniquely written in this form. So precisely of numbers of this type, where rk's are rational numbers and p is this Euler torsion of n. Okay. The action of G, so this, by the way, this is not an entirely trivial result. It requires understanding GCD for uh, polynomials. Okay, and something which is something which is called Gauss's lemma, which allows us to understand how to recognize. So just as we have a way to find prime numbers, so you want to have a way to find polynomials which are like primes, which are what are called irreducible polynomials, and how to recognize them. And Gauss came up with this theorem, which is known as Gauss lemma, which says that if a polynomial, let's say if I look at x squared plus x plus 1, or maybe I should start with x squared plus x squared. So let's look at this polynomial. So we can ask, how do I know that it cannot be factored? Or even classically, of course, one looked at x squared minus 2. So one looked at this proof. So Gauss looked at the proof given by Euclid of showing that this has no root, and used that to prove that, say, this has no root. So how do I know that this one has no root over rational numbers? Okay, so the whole point is Euclid proved that this has no root over rational numbers. How does one prove that this has no root over rational numbers? And Gauss's idea was to prove that under certain conditions, which this polynomial satisfies, if it has a root over rational numbers, then in fact it has a root over integers. And for checking that it has a root over integers is very easy, because for large values of x, you can see that it is going to be very positive. So you only need to check for small values, and those values you can do by elimination. Okay, so he developed these techniques, and using these techniques, he was able to work with such equations, and he was able to prove that Kn consists precisely of numbers of the form this sums of kth powers of zeta n, where k goes from 0 to p minus 1, where p is the Euler torsion. Okay. The action of Gn on Cn here, I should have said. So we already had an action of Gn on Cn. Remember that takes zeta n goes, or the zeta n to the k goes to zeta n to the ak, right? And a is an element of G, right? And this can be extended in the action of Gn on the field Kn. Okay, so in other words, from here you can go to sigma k is going from 0 to p minus 1, rk, zeta into the ak, and then one has to check, and this is what we checked, that this operation preserves addition and multiplication. Okay, so that requires some work to check, but it's in fact true, and that is another beautiful result, and then one wants to understand what are the things which are fixed under various subgroups of GM. Okay, so the statement is that KMN of course contains. So if I take the nth root of unity, right, and take its nth power, then clearly this is an nth root of unity. Right? So So it is of this type for some k, but in fact for k equal to 1. Okay. So you know that Kmn contains Kn, okay, but it consists precisely of the elements fixed by the subgroup which we described earlier, okay. And more generally, subfields correspond to subgroups of Gn. So notice this beautiful observation of Gauss, which is that subfields of Kn can be understood by studying the action of Gn and subgroups of Gn. Okay. So this idea of studying this field, which is called the cyclotomic field, by studying the action of Gn, was what was extended by Abel and Galois to other fields. Okay. So this is the idea of Gauss. So let's come to quadratic equations. I think our time is okay. So I think they have been giving me 1.5 hours, but maybe I will try to finish early so that if there are questions, I can answer them. Okay. So if L is a subfield of complex numbers and tau is a complex number, then the smallest field that contains L and tau is denoted by L round bracket tau. And okay. And suppose tau satisfies a quadratic equation. Then you can see that tau, the other root, note that this is the other root, right? If the sum of the two roots, if tau1 and tau2 are the two roots, you know that tau1 plus tau2 is equal to minus alpha. And so you can take tau to another root, and this extends to a field automorphism of L tau. So this is the starting point of trying to understand where group actions come into quadratic extensions. So we already saw how they come into cyclotomic fields, and here we see how they come into quadratic. And now we want to combine the two, and we want to understand which cyclotomic fields are obtained by successively solving quadratic equations. Okay. So this is what the idea is, that if Kn is to be obtained as a succession of such quadratic extensions, we see that Pn must be a power of 2. Okay. So because there are these automorphisms and each one gives an automorphism of order 2, so we should get a, and now comes a very nice simple observation from the formula which I gave to you for Euler totient, and that is that the Euler totient is a power of 2 if and only if n is 2 to the power something times a product of odd primes, where the odd prime is itself of the form 1 plus 2 to the power something. Okay. So these are what are called Fermat primes, right? So a prime is called a Fermat prime if it's of the form 2 to the power something plus 1. Okay. Now, if that something happens to be a multiple of an odd number, right? So if t is equal to a times b with a greater than 1 odd, then 2 to the power b plus 1 divides 2 to the power t plus 1, right? So 2 to the power, note that 2 to the power b plus 1 divides 2 to the power ab plus 1 if a is odd. Okay. Because u plus 1 divides u to the power a plus 1 if a is odd. This you have done in high school algebra, the standard way of doing this. And this shows that 2 to the power t to be a prime, you must have t equal to 2 to the power j for some j. So in fact, a Fermat prime is a prime fj of the form 2 to the power 2 to the power j plus 1. Okay, so these are the only primes that will occur in with the property that the Euler totient is a power of 2. As of 2021, the only known Fermat primes are, there are only finitely many known Fermat primes. Okay, so in fact, it's kind of surprising. Originally, people Fermat maybe even thought that there were many Fermat primes, but Turns out that there are only finitely many so far. Okay. All the others, numbers of this type, uh, are not prime. Okay, so f5, for example, is not a prime. So let me say, how do you go about extending the idea of the construction? So Gauss, in fact, was able to construct with 17 gone. Okay, so note that 17 is one of these numbers, and later using Gauss sums, he was able to extend this idea to construct all fj-sided regular polygons. So of course, I mean, the point I want to emphasize is that this was a heuristic idea that because it's quadratic, succession of quadratic extensions, phi must be a power of 2. But in mathematics, that's not enough to have a heuristic idea. We have to actually have a proof. So suppose phi n is a power of 2, then can we construct the corresponding n-sided polygon? And Gauss actually constructed it for the case n equal to 17. Okay, where n minus 1 is 17 is a prime and 17 minus 1 is 16, which is 2 to the power 4. And so we do expect to construct such a polygon. And Gauss was able to extend this idea to construct all fj-sided regular polygons when fj is a prime. And in fact, more generally. Okay.
Sir,
I mean, yes.
when we are saying able to construct, I mean, did he prove it is constructible, or did he like construct?
Well, he gave the general what you can call an algorithm schema, right? So he provided a way in which one can reduce the problem to successive quadratic equations. So I don't know how explicit you want it, because obviously once you
No,
want to
like,
do
I
it,
wanted like we can construct a triangle, pentagon.
yeah.
We have a method. So is there
We
a
have a
method?
method, right? So it's a method, but it's a parametric method, so to speak, right? So you have to iteratively do something,
Okay, sir. Got it.
because you are doing it for infinitely many n. So that means for each n you have to write
I
down a
was talking about
succession of
70.
quadratic equations,
Yeah.
right?
Just
So
talking about
even
70.
17 he actually constructed, and even
Using
257 I think somebody after him constructed using ruler and compass, actual compass. Okay, but
using actual rulers and compass. Oh.
right. I mean, it takes a lot of work, by the way. So you have to be very patient. But you should remember that Gauss was extremely patient. He calculated by hands, I think, all the primes up to 10,000 or something like that. Okay, so he was an extremely patient man, and very systematic. So I would imagine that he would be able to do it. Yeah, but 257, I think somebody else did, and he was not a very famous mathematician. I mean, just he worked very hard. Okay, so yeah, so in any case, the idea is there. How I think Gauss gave the basic idea of how to write down. I mean, it's like saying you can solve every linear system of equations, right, by doing row reduction. But actually carrying out the row reduction requires you to write some loop and do lots of operations and so on. So Gauss gave various ways of simplifying the equations and so on using Gauss sums and so on. So we'll see some examples of this shortly. And one can extend this to 2k fj by repeated angle bisection and so on. And Mansell showed, in fact, Gauss claimed, but apparently he didn't write down a proof, which is somewhat surprising, and showed that uh, this zeta p cannot be constructed with quadratic extensions if p is an odd prime, which is not a Fermat prime. Okay, so that is another case where you could have asked the question: Is this all the cases? And in fact, these are exactly all the cases. Okay, so this result seems rather negative because it means that many n-sided polygons cannot be constructed. Okay, so we can ask the reverse question. Suppose you could construct n-sided polygons, what all can you construct? Okay, so we know that lots of n-sided polygons cannot be constructed, but we could turn the question around and say, suppose you can construct n-sided polygons, what other numbers, what other things can we construct? Okay, so that's what I'm going to talk about during the rest of this lecture. So a generalized protractor would allow us to divide a straight angle, by which I mean 180 degrees, into whatever fractions we desire. Right, which is the same as saying that you can construct zeta n for all n. So you take the numbers of the form zeta n for all n, and what are the numbers that we can construct using them. Okay, so using such an instrument, what numbers could be constructed? Okay, so what types of equations can we solve using zeta n for various n? And so the first non-Fermat prime is 7. So as before, you can check that zeta 7 satisfies this equation: t to the power 6 plus t to the power 5 plus t to the power 4 plus t to the power 3 plus t squared plus t plus 1 equals 0. Right? And as in the case of t equal to 5, you take zeta 7 plus zeta. I mean, maybe this looks mysterious, but from group theory, I hope it's clear that it's 6 is n minus 1, right? 1 and n minus 1 are definitely co-prime to n, and so you're taking to the 7 minus 1. Okay, so you look at this and you calculate, right? So tau squared is zeta squared plus zeta to the 5th plus 2, and tau cubed is zeta to the cube plus zeta to the 4th plus 3 times zeta plus zeta to the 6. Okay, just do the calculation using the identities which you already know. And now using the identity which it already satisfies, we just check that tau cube plus tau squared minus 2 tau is equal to 1. Okay, so it satisfies this equation, and so this means
Can I
that
repeat the
we can
quadratic
solve this.
equation? Oh, thank you. Thank you. This is a cubic, sir.
Yeah, so this cubic equation we can solve.
Okay, means there is no quadratic which satisfies.
No, of course not, because we said that if it has to be solvable by quadratics, then it has to be of the Fermat type. And 7 is not Fermat type.
Yes, but we can construct 7 gun.
So I'm saying the other way around. Suppose we can construct 7 gon, what equation can we solve?
Okay, so since we can construct a 7 gun, therefore we can solve this equation.
Exactly. So we can solve this equation. Okay, in terms of zeta n. That's what you're saying. It's given by this equation, right? So this is an equation which you can solve in terms of 7. Okay. So this is an equation of degree 3 that can be solved using zeta 7. But in fact, you can, if you want to write something neater looking, then you can also solve this equation. Okay. And you can check that it has this solution. Okay. So both of them give the same field, but the equation here looks, it's clear that there is a 7 somewhere, so maybe it looks nicer. Okay, next you can look at n equal to 8, right? So zeta 8 is the square root of I, so it can be constructed, of course. And in fact, if tau is equal to zeta 8 times 1 minus I, then you check that tau square is 2. And so constructing zeta 8 is the same as constructing a square root of 2, which of course you have learned how to do in high school. Okay, so zeta 9 on the other hand satisfies this equation, okay, right? Because zeta cubed is zeta 9 cubed is omega, right? Is a cube root of unity, and so it satisfies this equation. And so if you put tau equal to zeta 9 plus zeta 9 to the 8th power, then we check that tau cubed has this satisfies this equation, and from which we see that tau satisfies this cubic equation. So there are certainly cubic equations and perhaps higher degree equations, so which can be solved. So they can't be solved using ruler and compass, but if we allow ourselves to have a protractor which has arbitrary divisions of 180 degrees into equal angles, then we can actually solve various cubic equations, and maybe other equations. So the question is, what equations can we solve using this? Okay.
Sir,
So yeah,
sir, so like what I'm saying is that if say a number is means some number is a root of a equation and the number is not constructible, that complex number.
right,
So can we say that that equation is not solvable? We know it to be a fact that it's a root of this equation.
right.
So can we
No,
say
no.
that?
So we are saying that suppose we are given, just as we are given a ruler and compass, we are given one more instrument. The instrument is one which takes a protractor and divides it into equal angles. Now, how you construct the instrument is up to you,
No, sir, I'm
right?
asking a very different question.
Right,
I'm saying suppose we are given a number alpha,
right.
complex number, which cannot be constructed. Cannot be. We know it. But
By what? By ruler and compass.
ruler, no, yes, ruler compass, straight edge compass.
Right.
It cannot be constructed. And also we know a polynomial p, which
Ah,
of which alpha is a root.
sure.
So is p of alpha means not solvable?
No, no. One has to see what does it mean for it to be solvable. Solvable means what? Alpha is given to you, then of course you're already given alpha. The question is, if you have got an equation, the question is what are the equations which you can solve by using a protractor?
Okay, sir.
Okay,
No,
just as we normally look at what are the equations you can solve using ruler and compass, and now looking at what are the equations you can solve using protractor.
okay, sir. Thank
Okay,
you.
so yeah, the notion of what is constructible is a very tricky one, right? I mean, after all, you can say what does it? Why do we want to build in a physical thing like a compass and ruler into geometry? Okay, what does it mean for a solution to exist? So these are different questions, and maybe we can think about them. Okay, but right now let's go ahead. Okay, so now applying Galois theory, one can show that a field inside Kn is precisely the field of elements fixed by a subgroup of this group Gn, which we have been talking about. Okay, it's precisely the fixed field, and in fact, more than that, one can show that the automorphisms of this field are precisely Gn mod H. Okay, and all this was shown by Galois. I mean, rather, it's a special case of Galois theory, and uh, and a subfield of L fixed by H prime is exactly the field of rational numbers. So there's a group theoretic structure. There's a natural correspondence between subgroups of Gn and subfields of the cyclotomic field. Okay, so this is the question is what are all such groups of the form Gn mod H? And the answer is, in fact, every abelian group is of this form for some n, okay, and for some h. In fact, there are infinitely many infinitely many n and infinitely many h with this property. Okay, and this theorem is a kind of combination of two theorems. One is called the fundamental theorem of abelian groups. Okay, the structured theorem of abelian groups. And the second theorem is infinitely many primes. Congruent to one model. So both of these can be used to prove this statement. Okay, and so there are infinitely many mutually coprime n for which this can be done. So there are lots of these groups, and so there are lots of these fields which you can construct. Okay. So the idea of Kronecker and Weber was to use number theory developed by Kummer, Hasse, and Minkowski to show the following result is true. The following result. If L is a field whose automorphism group is a finite abelian group with fixed field Q, then it is contained inside Kn for a suitable n. So what they are saying is, suppose I knew that L, the automorphisms of L is a group which is abelian, and which is finite and whose fixed field is exactly Q, then this field L is actually a subfield of Kn for a suitable N. This is a beautiful theorem because it says that tells you exactly what numbers can be constructed with protractor. Right? With the generalized protractor, it says that any such extension or any number in this field can be constructed using a generalized protractor. Okay? So this is the answer to the question I raised. Of course, this doesn't mean that we can also ask, are there numbers which are not like this? And there are. And for example, cube root of 2 is a field which has no automorphisms other than identity. And so it's not a subfield of Kn for any n. And the classical geometry problem called the Delian problem was of doubling the cube, which is the same as giving a construction of cube root of 2. And so one cannot double the cube using a protractor. So there are problems which cannot be solved with a protractor, and it is worthwhile exploring. So this is maybe an answer, partial answer to the kind of question which you are asking. So what are the tools that we need in order to solve equations beyond ruler and compass? So remember that ruler and compass is basically solving linear and quadratic equations. So is there something else that we need in order to understand more general equations? What are the kind of tools? How complicated do we want to make things in order to solve? So suppose I want to solve an equation of degree 7. Is it true that I can always solve it by solving particular types of equations? Right. So this is the kind of question which Galois theory leads us to an answer, and in some sense, the answer is complete, and in some sense, the answer is completely incomplete. Okay, but explaining that will take yet another lecture. So let me stop here and see if there are any questions.
Thank you, sir, for this wonderful talk. If anybody has any questions, they may unmute themselves.
What is the exact notion of constructible using rulers and compass? Means the exact definition, sort of.
Yeah. So if you like, you can take the rational numbers, and
Yes.
to that you look at all the fields which can be obtained by successively adjoining roots of quadratic equations.
Uh, Please, I do not know what fields means.
Sorry, did you understand?
No, no, I mean, please repeat this.
No. So take the adjoin the root of a quadratic equation, then adjoin the root of another quadratic equation whose coefficients are in this new field, and then adjoin the roots of quadratic equation which are in this new field, and so on. And you are allowed to, of course, take only finitely many steps. And if you repeat this, then
So it's
what
like
you get,
constructible in a field.
these are the numbers which are constructible. These are the points in the plane which are constructible.
A constructible and the coefficients of the quadratic equation must be in.
Yeah, so you have to construct the coefficients of the quadratic equation, then you can construct the new number. So each stage you construct the previous coefficients of the previous quadratic equation, like we did for 5. So if you remember what we did for 5, right? We had first we took the solution of t square plus t minus 1, right? And there, of course, the coefficients are already constructed. And now we have to construct something like t square minus tau t, I think, or 3, something like that, plus 1 or something. I forgot what it was. Okay, so or 3 years. So you can repeatedly construct newer and newer numbers by repeatedly solving quadratic equations. But the point is that if you can, this doesn't give you all possible constructible numbers. I mean, this doesn't give you all possible numbers. So the constructible numbers are only these.
Okay, so like which has means the set of constructible numbers must be solvable by a quadratic equation. Or
Repeatedly. So you have to, in addition, so think of the way in which you say what are rational numbers. Rational numbers are repeatedly you solve linear equations.
yes.
Okay, but in the case of quadratic equations, you'll have to repeatedly solve linear and quadratic equations. So you can ask, suppose I repeatedly solve linear, quadratic, and cubic equations, what will I get? So that would have been a different approach to this lecture, but instead I asked if I allowed to solve uh, nth roots of unity. If I'm somehow allowed to find nth roots of unity directly by using a protractor, what are the things I can solve? Okay, and the answer is you can solve quadratic equations and certain types of other constructible equations. Okay,
Equations.
so we gave some examples,
Okay, sir.
and we also gave examples of some numbers which cannot be constructed like this. So the possibility still exists of looking for new tools to construct roots. Okay, yeah.
Yes.
See, one thing I should say here, of course, there are many ways in which, I mean, I don't know if you have heard this theorem, it's called fundamental theorem of algebra, which says that any equation has a root over complex numbers, right? So any equation in one variable has a root over complex numbers. This is a theorem, perhaps due to Gauss also. I don't remember. No, maybe not. Maybe Liouville's theorem. So in any case, it's known. Okay, but the point is that those theorems are existence theorems. They use analysis, and so what it really says is that you can find arbitrarily good approximations of the roots of a certain equation using complex numbers. Okay. Now that's not the same as saying that you can solve the equation because it's analysis. So you can find smaller and smaller neighborhoods of the solution, and now by shrinking the neighborhoods, we will know that the intersection will be a single point, and so we got it. But in some sense, that is not a construction as such. In fact, the typical proof is not even constructive in this sense. The typical proof is suppose the solution doesn't exist, then you get a contradiction. So this is not a construction at all. Okay. So, however, you might say, what is the use of such a theorem where you just prove the existence? Okay. So my point is that once I know the solution exists and has certain nice mathematical properties, I can use those properties to study the solution and the behavior of that solution, like we are studying this field. And you can use that behavior to track the solution down. You know, it's like saying, suppose you were doing wildlife trek, and somebody told you, you know, in this forest, which is 900,000 acres, there is a tiger somewhere. Now, just because you know there's a tiger does not really help you. But then once you know it's there, you can try to find ways to track it down and maybe find it. There are situations in mathematics where existence theorems cannot be made more constructive. But number theory is one of those where one can try to construct tools to find the solutions constructively. In some sense, I mean, what construction means will vary from person to person, but at least you can try to track things down more closely than what is given by just an existence theorem, which says if the solution doesn't exist, we get a contradiction. So therefore, the solution must exist. That is not a very, that's a useful theorem, but useful in the sense like the tiger in the forest. It exists, but actually going into the forest and managing to get a picture of the tiger is an entirely different story. Okay, maybe I've spoken enough. Any other questions?